Hi, welcome to today's video about Sun-like stars, the G-stars. This is the closest system with a Sun-like star to the Sun. That's the system Alpha Centauri. The main star, Alpha Centauri A, is a G-type star like the Sun with 1.1 solar masses. Second star is Alpha Centauri B, which is a K-star with a bit lighter than the Sun. And there's a third star, that's star C, Proxima Centauri, is a red dwarf with just 12% of the Sun's mass. The system has an age of 4.85 billion years. It's about 1/4 billion years older than the Sun. The distance of the two main stars changes between 11 and 36 AU, over the period is 79 years. And red dwarf orbits these two bigger stars every 550,000 years. And this is interesting candidate 1, also called Alpha Centauri AB. That's an unconfirmed exoplanet candidate. Its mass could be between 20 to 50 Earth masses, with probably a gas giant. It is right in the habitable zone of this G-type star, Alpha Centauri A. And the question is, could this planet have habitable exomoons? This is a very good candidate for future observations with the James Webb Space Telescope. This is the internal structure of a G-type star like Alpha Centauri A or the Sun. The Sun's core is where the hydrogen fusion happens. The temperature is 15.7 million Kelvin. What's very impressive is the mass that's converted into energy. So 4 million tons of matter is converted every second into energy. The photons need about 170,000 years to escape the Sun. And the neutrinos are much faster because they barely interact with matter. And the Sun-Earth distance is 50 million kilometers. That's 1 astronomical unit, 1 AU. That's 8 light minutes. You can see here the core, then the radiative zone. And outer zone is the convective zone. The convective zone is like boiling water. That's heat transport by transport of matter. This is a nice animation of the life cycle of a G-type star like the Sun. You can see the G-type stars have differences in age. Some are much younger than the Sun. Some have age more than double the Sun. And with age is related to metallicity. The older stars have a lower metallicity. Metallicity is a percentage of elements other than hydrogen and helium. And Sun-like stars are known for their luminosity increase by 1% every 100 million years. This has the effect of on the habitable zone. The habitable zone over time moves slowly further out. The main sequence lifetime of a Sun-like star is 10 billion years. Then they will become a red giant. And then they will lose about half their mass into space, and the other half will become a white dwarf. This is what happens to the planets that are near an expanding star. A G-star, when it's at the end of its main sequence lifetime, the inner planets will spiral towards the expanding star and eventually be swallowed. And this will happen to 3 of the inner planets of the solar system, Mercury, Venus, and Earth. Mars is far enough. This is one example. That's R Sculptoris. That's a variable giant star at 1,440 light years distance. It has 139 times the size of the Sun and a carbon-rich atmosphere. This is one example of a star which is near the end of its main sequence lifetime. Its shell has been ejected. And this is the far future of all G-stars. This is called the G-dwarf problem. That's the fact that there's a small number of G-stars with low metallicity. And it contradicts the closed box model of the Milky Way galaxy. And the solution is there's a continuous accretion of gas into the galaxies. That's how this small number is. That's the explanation for the small number. And the same phenomenon exists for the lighter types of stars, the K-type stars and the red dwarf stars, the M stars. This is another example of a G-type star, that's Tau Ceti at 12 light-years distance. That's 78% of the Sun's mass. It is much older than the Sun with an age of 8 to 10 billion years. Its luminosity is about half that of the Sun. And this system is known to have 10 times more dust than the solar system, as a debris disk at 10 to 55 astronomical units distance. And it is a promising candidate for Ceti missions because it is a Sun-like star. Tau Ceti is known to have 4 confirmed planets, and there could be 4 more candidates that could also be planets. These are 2 examples: Tau Ceti E with more than 4 Earth masses, orbital period 162 days, calculated temperature 68 degrees Celsius, and Tau Ceti F, another super-Earth with minimum mass of 4 Earth masses, orbital period 636 days, calculated temperature minus 50 degrees Celsius. These temperatures are only estimations. For the real surface temperature, the atmosphere is important. So theoretically, both these planets could be habitable potentially. This is another example, 61 Virginis. This is another G star at 28 light-years distance. It has 93% of the Sun's mass. It is also older than the Sun with 6 to 7 billion years. Its luminosity is just 82% of the Sun. The rotation period is 29 days. So the Sun's rotation period is only 27 days. So there is a relation between age and rotation period, because over time the star loses the momentum to the stellar winds. That's why this older star, 61 Virginis, has a slower rotation than the Sun. So, but this star is known to have a Sun-like composition. So if this is a Sun-type star, imagine if somebody would look towards our solar system from this place or from another place which is 30 light-years away towards the Sun, you would see the same bright star in the sky, the Sun. And this system is also known to have a debris disk at 10 to 55 astronomical units. It's a promising candidate for Ceti missions. This is one of the planets, 3 planets within half AU of 61 Virginis. That's a super-Earth, 61 Virginis B with 6 Earth masses. And there are 2 Neptune-type planets, Planet C with 18 Earth masses and Planet D with 11 Earth masses. And there could be another habitable planet too, in the habitable zone of this star. This is another G-type star, TOI-199, at a distance of 322 light-years. It is a bit more massive than the Sun, 10% more massive. It is a very young star with an age of just 800 million years. It has 2 Saturn-type planets. One is 17% of the Jupiter's mass, or Planet B, orbital period 105 days. Second, Planet C is more massive. It has 28% of Jupiter's mass. Orbital period is 274 days. That planet is in the habitable zone. And simulations have shown that this giant planet could have exomoons with stable orbits. This is another system, TIC 279401253, another G-type star at 931 light-years distance. It has 1.1 solar masses. Its age is 1.2 billion years, so just 1/4 of the solar system. It has 2 gas giants which are in a 2-to-1 orbital resonance. Planet B is 6 Jupiter masses, orbital period 77 days. Planet C with 8 Jupiter masses has an orbital period of 155 days. And both these planets are not in the habitable zone, they are too close to their star. This is another G-type star, Kepler 1513, 1150 light-years. Is about the same mass as the Sun. As a Saturn-type planet, Kepler 1513b at 0.53 AU, orbital period 161 days. And there was an Exomoon candidate, but it was not confirmed. And now theory is that there might be another Saturn-sized planet nearby. It would be Kepler 1513c. This is another system that's not a G-star but a K-star, but it's not so different from the Sun. That's HT 11067 at 105 light years distance. 30% of all stars are K stars, a bit lighter than the G-type stars, the sun-like stars. The star is just 80% of the sun's mass. Has 6 sub-Neptunes within 0.26 AU. So this means all these planets are not in the habitable zone, they are too close. They have a mass between 4 to 9 Earth masses. And what's interesting is that more than half of all G-stars, sun-like stars, have these kinds of planets, sub-Neptunes, in close-in orbits. This is this overview of the system HT 110067. The stability of the system is due to orbital resonances. For example, B22 between planet B to C, B22 between planet C and D, and the innermost planet, planet B, has a 6:1 orbital resonance with the outermost planet G. That explains the stability of the system, HT 110067. There's another interesting system, that's WASP-39. That's a G-star at 700 light years distance. 0.7% of sun-like stars have a hot Jupiter, like WASP-39. This is WASP-39b, that's the planet. The first planet gets always the small letter b, then C, D, etc. This planet has 28% of the Jupiter's mass. The orbital period is just 4 days. The current theory for the hot Jupiters is the migration theory. They were formed further outside and then migrated inwards. And the question is, can a hot Jupiter system still have a habitable planet in the habitable zone or not? This is not clear yet. There's another very interesting system, that's HIP 11915. That's the Sun's twin at 190 light years. It has about the same mass as the Sun. It's about 500 million years younger than the Sun, with the age of 4 billion years. This is how the companion of the star could look like. That's a Jupiter twin, HIP 11915b. That's 4.8 AU distance, so almost the same distance as Jupiter from the Sun. The orbital period of this planet is 10 years, and this system is a candidate. It could have a Earth-like planet at the habitable zone at 1 AU. And this is a AI render of a potential Earth-like planet that would be the planet HIP 11915c. This is a very beautiful AI-generated image of a potential habitable world. And that was today's video about the Sun-like type stars, the G-stars. You can check out the links to the scientific articles. Thank you for watching. Have a nice day. Bye-bye.